Hi class, this video is on topic D5, the motor principle and the DC motor. And the learning goals for this lesson are to be able to state the motor principle, use right-hand rule number 3. Yes, we have another right-hand rule. And that you can label a DC motor with its components and describe the function of each of those components. Describe the factors that can improve the DC motor. So it's understanding of the motor principle and the DC motor that are the focus of this lesson. So in the early 1800s, Michael Faraday decided to design an experiment that posed this question. Can a magnetic field cause a current-carrying wire to move? And he found that the answer is yes. So in this setup, notice that if there's a switch here, and notice that if that switch is closed, there is a closed circuit loop if you include the liquid mercury. So the current, we could think of it as coming out of the positive terminal of the battery, going through the red wire, and then going up this metal stand and down through this dangling wire, which is sitting in liquid mercury, and then connects down here, because this is all electrically conductive, going down through the black wire up to the negative terminal of the battery. So it makes a full complete loop. Liquid mercury is used here because since it's a metal, it's electrically conductive. And so the current will actually form a complete loop. And then also, most metals are solids at room temperature and pressure, but mercury is a liquid. And because it's a liquid, it allows the wire to move easily if there's a force on the wire. And that's what we're trying to determine if the wire can move. So we must be able to give it the freedom to move by putting it in the liquid. So when this switch is closed, he observed that the wire started to twirl around the permanent magnet that was sitting in the mercury. And the wire only does this if there is the permanent bar magnet sitting in the mercury. And this means somehow this magnetic field, this external magnetic field, it's external to the wire's magnetic field, because we know once there's current through the wire, there's going to be a magnetic field around the wire. But the external magnetic field created by the permanent magnet is causing a force on this current-carrying wire. And so Faraday's experiment demonstrated that an external magnetic field can cause a current-carrying conductor to move. And this is considered the first electric motor. So now let's talk about the motor principle, which formalizes this observation. When we set up a magnetic field with 2-bar magnets, just like this in this diagram, with north on the left and south on the right, and then we place a current, a wire with current going into the page, recall that the X is into the page, we get a force on the wire that is downwards. And if we were to switch the north and south poles, then we would get a force up. Or if we were to switch the current direction to a dot out of the page, then the force would be up. But if we were to change both the magnetic poles and the current direction, then the direction would be down. So there's all these different combinations of the direction of the magnetic field lines, the current, and the force. So the formal statement of the motor principle is that the current carrying conductor that cuts across an external magnetic field or external magnetic field lines experiences a force perpendicular to both the magnetic fields and the direction of the electric current. So first of all, perpendicular to both, we've got 3 things. 1, 2, 3. So we've got the force, the magnetic field lines, and the current. 3 lines in 3D space all being perpendicular to each other. Maybe in math, you've seen where you have an X and a Y and a Z axes of like a 3D graph. So here we have north to south is one line. So what's 90 degrees to that? Well, it's in and out of the page. And then what's 90 degrees to both up and down and in and out? It would be left to right. So you've got north to south, left to right, and then the current is in and out of the page. So in this diagram here, there's going to be a force on this wire, according to the motor principle. There is a force on this wire. And what is the direction of that force? It's either right or left based on the perpendicular word. It's perpendicular to both. So our answers are either right or left. And in this case, the answer is to the right. So one way that you can determine the direction of this force is by looking at the neighboring magnetic field lines. So if you look at the magnetic field lines that are created by the fact that the wire has current, so this line here, and its neighboring magnetic field line, because of the permanent magnet, is opposite to the direction. So opposite magnetic fields, there's an attraction here. As we were talking about in the last lesson, we were talking about you might want to use the direction of neighboring magnetic field lines to determine outcomes. On this side, the magnetic field lines are in the same direction. So there's repulsion here and attraction here, and both of those will have an effect of moving the wire to the right. And there is another way. There is a mnemonic device that tells you the relationship between these three directions. And that mnemonic device is called the right-hand rule number 3. So the good news, and maybe the bad news, is there's another right-hand rule to memorize, but the good news is that it looks very different, so I feel like it's easier to distinguish. The other difference is that there are 3 things to keep track of here, whereas right-hand rule number 1 and 2, there were only 2 things, the current and the magnet, to keep track of. Here we have a current, the magnet, and the force. So you're going to actually, if you did right-hand rule number 2, it would be like that, but now let your fingers uncurl so they're flat and your palm is flat. Your straight fingers will point in the direction of external magnetic field lines. So I think of my wrist is north and my fingers are south, because we know magnetic field lines go north to south. And then the thumb points in the direction of conventional current. So this is positive to negative of the battery. And then the palm shows the direction of the force on that wire. So your palm in this diagram is up. And that's what it looks like, just taking a closer view. And if you just do that position with your hands and kind of just observe in 3D space that if your thumb is all the way out like this, there is a 90 degree between your finger direction, your finger's direction, your thumb direction, and your palm direction. So those 3 directions are 90 degrees to each other. So just to kind of sum up what I was saying about those diagrams, there's 2 ways to solve them. One is to look at the neighboring magnetic field lines. And to do that, you would have to use right-hand rule number 1 to figure out this circle. And then the regular magnetic field lines rules to figure out these semicircles here. And then you're going to look at the neighboring magnetic field lines, and opposite neighboring magnetic field lines is attraction. Same line, same direction magnetic field lines will be repulsion. So that was the first way. And the second way is right-hand rule number 3. So right now I want you to use the hand gesture of right-hand rule number 3. You're going to put, well, the order that you do, the order that you solve these problems in, it doesn't really matter. But what I like to do is I like to do the magnetic field lines first. So take your wrist and put it near north, and then you're gonna point your fingers down at south. Then your thumb is gonna come out at you, because this dot means out of the page. So you're looking down your fingernail, and then notice how your palm is pushing to the right. So that's how you would solve using right-hand rule number 3. So let's try a few examples So I will give you a big tip. So actually this probably was not that comfortable, and I don't want you to all get carpal tunnel syndrome from this. So the tip is you can always rotate your page so that north is always, north and south is always natural for you. And then your thumb out at you or your thumb into you, it's just rotating at the wrist or the forearm, and that's not too uncomfortable. It's like doing the single ladies dance, you know, think going into your inner Beyonce. So it's not too bad just to rotate at the forearm. Your thumb is either in or your thumb is out. Okay, so let's rotate the page to see if we can do these three problems a bit more comfortably using the right hand rule number 3. These examples are the ones that are in your student notes package. Oops, 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 oops. Okay, we're just gonna scan over those. So example number 1, part A, you're gonna rotate your page around that way so that your wrist can be at north, your fingers are pointing up at south, then your thumb, do you remember what the X is? So the thumb is gonna be pointing into the page, and notice that your palm is to the right. The next one, we had to rotate it, oh, I guess this is upside down. Okay, we're rotating our page so that north is at the bottom and south is at the top. So I haven't changed anything about this diagram. I just rotated my page around so that my thumb, my wrist is more comfortably at north and my fingertips are pointing straight up at south. Then your thumbnail is out of the page, so you're looking down your fingernail, and notice that your palm is to the left. Our last question. We've rotated it all the way around so that north is down and south is up. So I place my hand there. Now notice that we're given the force, and what's missing is not the force. What's given is actually the current direction, either a dot or an X. So north to south, I place my wrist and my fingers there. In order for my palm to face to the right, do you see how your thumb has to be going into the page? So it has to be going in. So if you look at the answers upright, this is what you would get. And it's really important to practice these. Oh yeah, we're using our right hand. So for those of you who are left-handed, you have a little bit of an advantage, but if you're right-handed, you had to put down your pencil and do the right hand rule, and then determine the answer, then pick up your pencil and write it. So just be warned that it's tempting to use your left hand instead of your right hand if you are right-handed. I know I do it all the time. So if you're left-handed, you have a bit of an advantage. So let's talk about some of the advantages of some of the applications of the motor principle. So the first application is loudspeaker. So this is for like a speaker that would produce bass notes, so subwoofer or a tweeter, not like a small headphones because of the high-pitched tones that you would get. So for a loudspeaker, you have a base magnet and then you have a cone with wire wrapped around it. So you recognize this. This is going to be an electromagnet. When we have current running through the coil, there is going to be an attractive or repulsive force that's going to push the cone into the base of the magnet or repel it out of the base of the magnet. And since the current that we use here, it is alternating current, which if you remember, that means the current can change direction. For example, if we change the current direction 140 times per second, that would be called a 40 hertz AC current. Then the force would go up and down 140 times per second. And these vibrations of the cone are what cause a sound wave. And in the case of this example, it would be at a 140 hertz sound. So each frequency has a different pitch, and we're going to learn a lot more about that in the sounded waves unit. Another application is called the galvanometer. So obviously the loudspeaker, the purpose was to produce sound. galvanometer, the purpose is to measure the amount of current. So what you do is you attach, let's say if you have a circuit and you want to know how much current is flowing through it, you would attach to this galvanometer here and here, and that would divert or like bypass the current into this coil here. And this is a little electromagnet, so when there's current running through it, we create a north pole here, and the more current, the stronger the north pole. So depending on how strongly the north pole is created, it will attract the south pole here and rotate a little bit or a lot. So if there's a little bit of current running through it, the north, it will be a small north pole, and it will maybe be deflected a half a milliamp or 1 milliamp. And if there's a lot more current, it can go up to 2 milliamps, but this is only good setup for measuring a small amount of current up to 2 milliamps. So that's why we call it a milliammeter. As the current flows through the coil, the armature is just a word for this arm, so it's a coil that can rotate, is forced to pivot to the right due to magnetic forces. Okay, now let's talk about the DC motor, but I will say the best preparation for understanding the DC motor and what assessment questions you might be asked is to read the textbook. So first, what is a motor? So the purpose of the motor is to turn electrical energy into kinetic energy. And a direct current motor does this by utilizing a current that does not change direction. So that might not be amazing until you look further into it. So for example, you plug your blender into the wall, you've got electrical energy from the wall socket that turns into kinetic energy that rotates the blades to chop up your strawberries and mangoes and fruits and vegetables into your smoothie. So a DC motor uses an electric current to produce a magnetic field in a coil, and the coil starts to rotate in the external magnetic field. So you have your external magnetic field, and we're attaching to a battery. A battery is something that allows a DC current, direct current. So the direct current, it flows through this armature. And this armature is free to rotate around. So when there's current through a coil, there's going to be a north side of the magnet, which is it's going to rotate and try and line up. So let's predict the outcome here. If we send current through this coil and we create a north magnet here, and this arm is free to rotate, what will happen? So obviously the north pole is attracted to the south pole, so there will be clockwise rotation. But when it gets here, what will happen? The north pole and the south pole are facing, they're happy to be attracted to each other. They are happy in that position. With this design, there's no reason for the arm to continue spinning. That means in this blender, if this was a motor of a blender, you only get 1/2 revolution, which is maybe enough to slice 1 strawberry in half. So the blender is not going to make your smoothie. So the question is, how can you make the motion continue? So the problem is, how can we make the motion continue? And the solution is that we're going to change the direction of the current. So here, notice the current direction was that way on the coil. And then now look at the arrows, they've switched. We're going to switch the direction of the current. And now, using right-hand rule number 2, this side is going to be your north end. And now north and north are facing, which is a force of repulsion. So this arm was starting to go clockwise. There is some momentum that now this north and north, they don't want to be facing each other, and it doesn't matter how this gets away, whether it goes this way or that way, except just a second before this was turning that way. So the momentum helps keep it continue. North now wants to get away from north and face south. And just after that happens, we switch the current again. So we have repulsion, and then a 1/2 turn for attraction, and then we get repulsion again. So the formal solution is that we use a split ring commutator to change the current direction, which changes the magnetic poles. So let's take a closer look at this split ring commutator piece, which is a really important piece in the DC motor. So from here on, instead of having in our diagrams of our motors, instead of having a coil electromagnet with multiple loops, the textbook does this like one loop coil just to simplify things. So I'm using it here so you can follow along with the textbook. And if we only have a one loop coil, we're going to apply right-hand rule number 3. If it was a full coil with many loops, then right-hand rule number 2 would be easier. So to temporarily interrupt the current and change its direction, to change the direction of the magnetic field, we use a split ring commutator. The split ring commutator and wire are free to rotate around the axis. And then the circuit is incomplete when the loop is in line with the split. So there's a moment where there is an open circuit, and then the rotation continues. Brushes are made out of conducting wire, come in contact with the split ring commutator, but still allow for rotation. So this loop, along with the split ring commutator, is free to rotate around. So sometimes the pink side is on this side, sometimes the pink side is on that side. This piece is free to rotate around. The brushes stay with the wires, so stay in place, but allow there to be a physical contact between the wires and the split ring commutator. The split ring commutator is part of the DC motor and interrupts the circuit. It changes the direction of the current and the direction of the magnetic field, keeping the motor spinning continuously. So at one point, the current flows out of the positive terminal of the battery into the purple side and over here. But as soon as this rotates around, we actually want to switch that. So the gap is going to line up this way, and then once this rotates around, the pink side is going to connect with the brushes, and the current is going to go through the pink side. So every half turn, we're going to change whether the current is going through the purple side or the pink side. Purple side, pink side, purple side, pink side, and that ensures that there's always an attraction, or there's always a force continuously spinning that loop. Brushes make physical contact with the split ring commutator to complete the circuit and still allow for rotation. So I can appreciate that there's some visualization. You have to visualize the animation here. So I've tried to make a little GIF. So I've tried to come up with a sequence of diagrams that will help you visualize. A DC motor has a rotor magnet and a stator magnet. So here is the rotor magnet. This is the part that rotates. And here is the stator magnet. It's the one that stays. So the rotor magnet is an electromagnet. It's not always magnetic. It depends on whether there's current running through it. But the stator magnet is a permanent external magnet. So taking a look at the sequence of diagrams. So we've got, this happens first. This is a step we're going to go over in more detail. Then we've got another step. We're going to go over in more detail. Another step, and another step. So I'll do it a bit faster. So you can kind of see that counterclockwise rotation of the loop. Going back to the first diagram, I just want to, again, explain, if you're using just a single loop coil, you're going to use right-hand rule number 3. You're going to imagine that there's a cross section here. If the current goes through the purple side of the split ring commutator first, then the current is going back into the page. So you take your wrist, you align it with north, fingers point south, and then your thumb is going to point into the page. You get your palm facing down. So on this section of the wire, we're going to have a downwards force. Then if our current continues over here, if you were to do a cross section, instead of it being an X here, it would be a dot here. So it's coming out of the page. So again, wrist to north, fingers to south, thumb would be out of the page. Then your palm would face upwards. And both down over here and up over here support that's going to be a counterclockwise revolution. So I'm only briefly going to look at, well, I'm going to look at each of these steps in a little bit more detail. In step 1, we've got conventional current flowing positive to negative in terms of the battery, which is purple to pink in terms of the split ring. And then right-hand rule of motor principle tells you that there's a downwards force here and an upwards force here, which overall gives you a counterclockwise rotation. In step 2, it's the same as step 1. There's a little bit of momentum that is keeping that rotation. And then the moment that the split ring, there's a gap in the split ring that lines up with the brushes, there is no current running through here. But there is, I said momentum, but that is, when we get to grade 12, we talk about momentum, but it's inertia. Remember, inertia is that objects in motion are going to continue in motion until there's a non-zero net force. So this object in motion, in counterclockwise motion, it's going to continue along. You can think of it as momentum as well. So it's going to continue along. But then, do you see how the current, which was originally starting from purple, is now going to start in the pink? And using the right-hand rule motor principle again, we get downwards push and upwards push, which again results in counterclockwise rotation. So I highly encourage you to go to your textbook, page 568 to 569, and take a more detailed look at those diagrams and explanations. And just talking about improving the design better than that one loop design that we had in the diagram so far. If we use a soft iron armature in the middle and increase the number of loops in the coil, this will increase the strength of the motor. If you recall, these are things, they're related to how to increase the strength of an electromagnet from a few lessons ago. So instead of just having one loop, we're going to have many loops. So this is going to increase the strength of this electromagnet. We're also going to put it on a piece of iron that can rotate it around. Here is your split ring armature. Instead of being purple and pink, it's part A and part B. And yes, one of the main learning goals of this lesson was to be able to label all these parts and tell what is the function of each part. So we've got our external magnets, we've got our battery, we've got conventional current, we've got the split ring commutator, parts A and B, the brushes here and here, which make contact with the split ring commutator, and the coil of the wire, and the soft iron core, or you could say the armature, or you could say the arm. So make sure you know how to label and explain the different parts. When you are doing these DC motor practice problems, I encourage you to actually draw it in your notebook and start tracing the current with your pencil, starting from the battery, so positive to negative. So identify the positive side of the battery, write it, then you're going to draw your arrows, and your arrows are going to trace out, maybe I will just go to a laser pointer so you can see it a bit better. So you start from the positive side, go down and around. It enters the brush, one of the brushes, then the brush connects to this piece of the split ring commutator. Then it connects to the coil and it goes around like this. Then it goes back up through this piece of the coil, and then through A, and then up through the brush and to the negative side of the battery. So that is the path. And with that path, if you, since this is not just one loop, we don't use right-hand rule number 3, you'll actually use right-hand rule number 2 for a solenoid. You'll have that thumbs up hand gesture, and then you'll rotate so your curled fingers are actually along this line. So your thumb is pointing that way. You get a north pole here, and it's attracted to south. So that's explaining why there's a clockwise. This is a clockwise rotation. This is a diagram of a completed answer. So everything's already filled in, but what you might not have is you might be missing the direction that it turns. Or you might be missing the battery and you have to decide which was the positive or negative side. Or you might be missing which side was the permanent north or south magnet. So looking, how is this different than the other one? So notice that the current first goes through B and then through the coil. And then once north has moved clockwise for a little while, now the current is actually the current from the positive side of the battery. Let me get my laser pointer again. Positive side of the battery, it's actually going through A. Because remember, the armature and the split ring, they rotate together. So now we're in A, and it goes through around like this, up and around, and then into B, into the negative side of the battery. So notice how the current switched from going through B first and then going through A first, and that means that this side turned from north over here to south once it was passing by, and now there's a repulsive force moving it away. The previous diagram, there was an attractive force bringing it clockwise. Now there's a repulsive force continuing it clockwise. And then when south gets to about here, you can say now it's attractive clockwise. And then when it just passes here, it's going to be repulsive. So it's going to continuously be clockwise. So now you have some practice questions to complete. There are textbook questions. There's an optional worksheet to practice all of the right-hand rules so far. And one of the big challenges on assessments is to figure out which of the right-hand rules to even apply. So that's why it's good to have a worksheet where they're all mixed together. But it is optional. Make sure that you fill out the exit ticket for this lesson and make sure that you submit the practice problems once you have completed them. Have a great day.